Hi everyone, I am Paris. And in this part of the tutorial, I'm going to cover some fundamental aspects regarding state in data stream processing, and that includes interfaces for defining and manipulating state, as well as mechanisms that ensure good scalability and consistency guarantees for long-running data streaming applications. So first of all, what kind of state am I talking about? Typically, if you have worked with stream processing systems, you're probably aware of the general idea. So state is effectively what captures all internal side effects of a continuous stream computation, which includes, for example, active windows or partial and incremental aggregates, as well as possibly some user-defined variables created and updated during the execution of a stream pipeline. Now, state management is an active system subject that incorporates different methodologies regarding how state should be declared in a stream application or how it should be scaled and partitioned, perhaps different ways to make state persistent for really long-running stream applications, and more importantly, defining system guarantees and properties to maintain whenever a change in the system occurs. And that can be, for example, a partial failure or times when we need to reduce or increase compute capacity. And most of these issues are not that new. So they were actually covered several times already in the past. I would say Borealis already has been, for example, pretty pioneering because it formulated many of these problems way back and the need for embedded state, persistent store access, as well as failure recovery protocols. The state management has evolved substantially throughout the years, providing stronger and better guarantees. So as you can imagine, the applicability of data stream processing systems followed along with more and more critical applications adopting the data streaming paradigm over the years. So starting from approximate sensor analytics on transient state to more scalable, low latency web scale, yet non-critical applications. When the first distributed stream processing systems became mainstream, to what we have today, which is stream processing as the de facto standard architecture for production-ready transactional real-time apps. Today, it's quite common to see banks, video game providers, car sharing services, automated agriculture services using data streaming systems at scale to support critical yet low latency applications. Throughout this session, I'm going to cover, first of all, programmability of state, also partitioning schemes, strategies for persisting, infinitely increasing state, and finally, how transactional processing can be supported in modern streaming architectures. In the end, I'm also going to share a number of interesting prospects and directions for future systems research. So first, when it comes to state management approaches, there are differences to how the user and system interact with the actual state. So one has to declare and use the state, and also there's also the need for someone to be responsible for managing the state. There are two possible candidates here, the programmer and the actual stream processing system. In the early days of data stream management, when main memory was scarce, state had a more facilitating role, supporting the implementation of user-defined operators such as CQL's joins, filters, and sorting algorithms. The term used to describe that type of state was synopsis, which means summary in Greek. Typically, users were oblivious of its existence, and the stream processing system was internally defining and using that state while also choosing the right optimal data structures to back it up. Here you see two example pipelines, one in Stanford's stream system and one on Borealis. In both cases, special synopses were attached in the data flow graph, supporting different operators such as window max, a join index, or input source buffers for offsets. An interesting idea, especially in the case of streams on the left, is the ability of the system to compose complex synopses using other synopses. Therefore, this allows some type of state reuse of intermediate results, at least internally in the system, which makes sense since the system is fully aware of the whereabouts of state in any given application. In short, synopses have been one of the first forms of state in early stream processing systems, primarily for stream processing over shared memory. Several of the issues regarding states, such as fault tolerance and load balancing, were already considered back then, for example, in Borealis. Although what was really missing here was the existence of some declarative model for user-defined state. Furthermore, the use of over-specialized data structures was somewhat oblivious to the needs of reconfiguration, which requires state to be flexible and easy to partition. During the second generation of stream processing systems, there was a primary focus in compute scalability with systems like Apache Storm, for example, allowing the composition of distributed pipelines of tasks. For application flexibility and to keep things simple, many of these systems did not provide any state management whatsoever, leaving everything regarding state to the hands of the programmer, and that includes both declaration and management of state. A user-declared and managed state was either defined and used within the working memory and scope provided by the hosting framework, or defined and persisted externally using an existing key value storage or database system. In summary, application managed state is pretty flexible and it gives users a lot of freedom. However, there's no really state management needed from the system side. That means that the user should reason about scalability, processing guarantees, and all required third-party system dependencies. As to the state of the art in stream state management, and that's user-defined state that is actually managed by the system. The typical way to support this kind of state in today's frameworks is, of course, to provide users with a stateful processing API. On the left, we have a short user's example of Apache Flink's mutable state. And as you see here, the necessary steps needed by the user are, first of all, to define the type of the state, for example, single mutable value, and name my state here, and also provide indications whenever that state needs to be written or read using the update and value functions. Likewise, in Apache Beam, we can encapsulate complex types of states, such as index states, used to aggregate and serve user models within a streaming pipeline. In summary, system-managed user-defined state is the best of both worlds, allowing some level of flexibility in terms of the types of state that the user can declare, while also enforcing the system to manage it, such as doing partitioning, scaling, and making it fault-tolerant. Things we miss here are really custom types of state and user-level optimization opportunities. Flink, for example, supports only single value, mutable, append-only lists, and a map per key state. Task-level partitioning maps state to physical compute tasks, allowing one instance per task. And this is typically the best choice when we need to compute global aggregates, such as top K stream queries, or when the state does not grow over time. On the left, you see an example of a top K window count in the SAMSA system that is aggregating entries from a single store, the store object that you see here, and then it sends it over a window to select the top 10 entries. Another popular example of task-level state is the implementation of message queue consumer sources, which is very common in streaming pipelines. These are typically special tasks that subscribe to fixed brokers, for example, a Kafka broker. And task-level state is used to actually hold the current offset in each individual queue within the source. Task-level state can be useful for specific operators, but it is, of course, not the norm in stream applications. There are several reasons why. Most importantly, that's due to the fact that it's really hard to repartition that state, given that it always maps to a physical set of tasks. In short, key-level state is the main way to define scalable state in streaming systems. Key state allows logical level partitioning of state to compute tasks, where each compute task, like the one you see here, handles a range or set of state keys. This is supported in the API level through key by, for example, in Apache Flink, or group by operators, which are used, for example, in Beam and Kafka streams. Now, an obvious state management problem here is how many states can we hold in each task? Obviously, we can't just rely on main memory, especially when we deal with state that is growing proportionally to the number of distinct keys in an unbounded stream. And there are some standard system architectures used to support scalable state that can grow out of core. And one and most popular approach nowadays by most open source systems is the embedded state architecture, which is basically a shared nothing architecture where each compute task has some amount of memory and also lots of disk space available locally to read and write its own share of the computation. No remote calls needed whatsoever to access state. Another way to scale state accordingly is to let the system use an external storage system to persist state. This approach was popularized by Google's Millwheel, and that is based on Bigtable. And finally, another interesting category of scalable stream processors built on top of storage and database technologies, embedding stream capabilities on top of data stores. The embedded state approach is popular mainly due to the fact that local access assumes fast reads and reasonably fast writes as well. On the other hand, since state is embedded and not managed independently to compute tasks, it is actually trickier to reconfigure stream processors with embedded state, since a lot of coordination and shuffling is needed beforehand. Same applies to transactional guarantees, as we will see later. To give you a flavor of a real embedded state example, here we have Flink and RocksDB as a backend. Flink is managing compute tasks and effectively forwarding every read, write, or local checkpoint operation to a local RocksDB instance. RocksDB maintains an in-memory table with recent changes in state, so when a write or read arrives, it is applied there first. Mem tables in RocksDB are periodically flashed to disk in order of keys. So if, let's say, now the key we want to access is not in the mem table, then we have to start a sequential scan on disk through these committed files of states sorted by key, which are called SS tables. That means that reads might take a while, and that will take more than writes. To speed up the process, SS tables are typically compacted and also guarded against Bloom filters to avoid unnecessary scans when possible. Local checkpointing of state can also be made faster through enabling write-ahead logs. Now, embedded state tech, such as the RocksDB embedded database, is still not the best fit for stream processing. For example, since stream processors ensure non-concurrent data access for compute tasks, there is no need for low-level latching, which is natively supported by most embedded databases. Also, we're in the process of rediscovering database indexes, but in the context of stream processing to speed up complex stateful analytics such as graph processing or relational joins. A number of interesting backends have been popping up alongside good publications, such as the faster backend, as you probably have noticed recently. So let's just say this is a very active field at the moment, and there's a lot to come. Now, when it comes to external state management, Google's Millwheel that serves as the executor of the Google Data Flow service is a good example. Millwheel builds on the capabilities of Bigtable and Spanner, and that includes, for example, blind atomic writes. Tasks in Millwheel are effectively stateless, and they do keep some local changes in memory, but overall, they commit every single output and state update all together to Bigtable as a single transaction. And this means that Millwheel is using an external store for both persisting every single working state per key, but also all necessary logs and checkpoints needed for recovery and non-idependent updates. In general, the idea of external state is very interesting, mainly because it allows application state to scale independently to the compute workloads. Reconfiguration is supposed to be the fastest with this configuration, since no state is needed to be shuffled if the compute parallelism changes. In practice, though, this solution is mostly employed within managed services such as Google Dataflow, given the complexity to maintain and tune multiple systems accordingly. So finally, when it comes to embedded computing approaches, SStore has been one of the most impressive ideas I have personally seen so far in the field of stream processing. And it basically breaks down an unbounded stream computation into a series of transactions that are statically scheduled in HStore, a database, and written basically as an extension of that database. So think of a pipeline consisting of many interdependent tasks, and SStore would put several of these tasks into a transaction that covers part of the input and execute and group commit them using HStore's ACID transaction properties. Kafka Streams is another interesting take that combines embedded compute with embedded state. It is embedded compute since stream tasks attach to physical brokers in Kafka, while it's also embedded state since a RocksDB instance is allocated per task to support dynamic state. A few pros and cons on embedded compute. I would say it really depends on the capabilities of the storage system that this is implemented. On one hand, these approaches share the benefits and optimizations of the underlying storage system. while they also lack the event processing performance capabilities of dedicated stream processing systems. And now we head into the very last part of the session, which has also been more of the holy grail in this domain. Primarily, this has been the case since it is a hard problem to offer guarantees in a system that processes potentially millions of records per second, but also I would say has been a problem of defining what consistency really means in this context. In simple words, consistency has to do with providing processing guarantees at the face of failure, as well as any need for change in a streaming application. So changing or updating a running data stream application is a concept also known as reconfiguration. For example, if you want to apply a software patch or bug fix in your streaming job or scale out to more compute nodes, you need to be able to do so without worrying about loss of accuracy. The underlying relation between fault tolerance and reconfiguration has been highlighted by many works in the past, such as this influential paper that talks about an integrated approach to scale and recover tasks from failures. Back in Hadoop times, there was this idea of separating systems across layers. So Hadoop and transactional databases were production ready and could take all critical computation, while stream processing systems back then could only scale, but they didn't quite offer a clear set of consistency guarantees. So they were considered experimental and non-critical for real-time computation. For example, the storm system would bookkeep which events have been fully processed or not, and maybe replay events on a timeout in case something went wrong, which effectively offers no clear picture of what sort of level of consistency we can expect from these systems. Also, there has been no influential work in terms of formal specification of properties we can expect these systems to offer. At the same time, databases had formal guarantees. For example, we knew that a set of transactions would be processed using ACID guarantees, which includes atomicity across transactions, consistency for the valid states of a database, isolation in terms of concurrent execution, and durability on what can be recovered after failure. For stream processing, on the other hand, there was nothing concrete. We didn't have a unit of transaction. Plus, this vague term of exactly once was circulating, which actually confused practitioners more. So what does exactly once delivery or event processing or ordering even mean when we are talking about a distributed data flow system with dynamic states, output, and arbitrary interleavings happening at the same time? Now, if we zoom in a stream processor, we can see that it is a distributed system. It consists of different concurrently executing tasks. We have the source tasks that subscribe to input streams. We have sync tasks that commit output streams to the outside world, and pretty much every task in the system can contain its own state. For example, source tasks need to keep their current position of their input streams in their state. Now think that every action happening in the system causes other actions. Effectively, just a single record sent by a source contributes to state updates throughout the whole pipeline, as well as output events created by the sinks. If a specific action is lost or happened in a different order, this is problematic, right? If we zoom even further and try to observe the execution of a single task, P, in the system, it typically goes as follows. So P receives a record M, and executes its operator logic, which updates its local state, and then creates an output, in this case, records K and L, which are forwarded to other tasks downstream. If now our task P crashed while performing that action, then the system should somehow recover that lost task alongside its state and also reproduce the actions that were lost. However, this approach is not as trivial as it sounds. Let's say the system starts up a new task P quickly after the failure. How does the new process know which actions are complete and which are not? Was the message M fully processed before the failure? Did all the output messages arrive at their destinations? More importantly, what should be the state of the recovered process P? Now that we talk about actions, let us define types of transactions. Existing systems either make a transaction out of its action or a coarse-grained set of actions that we call epochs. Now, let us see how this works out. Millwheel, that we covered a bit before, is actually using a big table to commit a full action at a time for each task. The state of an action is basically its input, its state update, and generated output event. Committing each of these transactionally is also called strong production in Millwheel, and this is a powerful approach given that you have a good external storage solution, since it can even support committing even non-idempotent operations. Exactly once processing in this setting actually means committing its such action exactly once. Now, epoch level approaches make a compromise. Instead of committing actions, we could instead log our input and divide it into mini batches. So then we can instrument a system execution in a way that commits the state of the whole graph of operators, the whole system, after its epoch is processed. And if something goes bad, we can always roll back to previous state in the stream, since we have the logged input and also the logged states of the system corresponding to those inputs. Now, how do we do this atomic commit here? One way to do this is to strictly coordinate the execution of our stream tasks. We can employ a two-phase commit protocol, where the first phase is the actual processing of an epoch or mini batch, and the second phase involves capturing the state of the system at the end of the commutation. That is effectively the discretized streams approach that was employed by Apache Spark in the early days, and it's quite effective when we use a batch processing system architecture to do unbounded processing. The downside of this approach is that the fact that the useful computation occupies only a fraction of our task's time, since they do have to wait for all other tasks to finish their current microbatch. The Drizzle paper partially resolves that through chaining multiple epochs in a single atomic commit. Now, in order to overcome the overhead of strict coordination, we can also use distributed snapshotting algorithms, which are available off the shelf from classic distributed systems literature. What these algorithms do is that they first of all run concurrently to the execution of the stream processor or any system, and they acquire what we call a consistent cut in that execution, like this line that you see here. In this example, we have processes P1, P2, and P3, which are sending messages around. So these arrows are messages. And the causal order respecting line, the red line that you see here, describes the consistent snapshot on the right, which contains the states of the three processes, S1, S2, and S3, at the time this line is touching this process. And plus, it has a message here that was in transit during the snapshot. So you can think of that message as pending computation that you would typically put in your redo log in case of database recovery. The rest is just the states. Now, Naiad, which has been one of the most pioneering systems, I would say, in terms of semantics, supports consistent snapshots using a simplistic two-phase protocol. First, tasks are posed, including their input and output channels. And then at the second phase, all tasks and channel states are collected in a global snapshot. And then they resume normal operation again. And this makes sense, but in fact, there are also ways to get consistent snapshots concurrently to the execution of the system without posing anything. Now, Stanley-Lamport snapshots or unaligned snapshots are one of the most efficient way to obtain a global checkpoint of any distributed system. It is currently supported by several stream processors, such as IBM Streams and also Flink's experimental unaligned checkpoint mechanism. And the main assumptions here are the fact that we assume FIFO channels. We also assume strong connected graphs. And the core idea is basically flashing this little thing, the marker, into the regular stream of events in the system, and use that marker to separate actions that come before the snapshot and after the snapshot. So whatever comes before the marker should be before the snapshot as well. So here, P1 first receives the marker, and it commits its state while also recording events before it receives the marker back. P1 forwards the marker to P2, and then P2 snapshots its state. In the meantime, P1 receives a message here, and it logs it into the snapshot, but it keeps processing as before. Then P3 snapshots its state since it receives a marker, and the rest of the pending events are also received by P1 and P2, so they are also included in the snapshot. And then finally, the markers arrive back to the sending process, and the algorithm terminates. And we have this snapshot here. An easy way to think of this approach for database experts is basically that this is equivalent to a fuzzy distributed database snapshot, where states correspond to the actual records that are synced to disk, and messages that you see here correspond to the redo log used upon recovery. So we always have to replay these events when we recover or reconfigure, or whenever we restore the state from that snapshot. Now, the final variant used today is snapshots that align to the epochs. They're called aligned since this is a core addition compared to marker-based Shannon-Lamford snapshots. The idea here is that instead of logging input records, we could instead prioritize input streams that are expected before the snapshot during the execution, and thus end up with just states to restore and no redo log whatsoever. So let us run this pretty quick. So everything is processed as usual. Markers are separating the epochs, and first, task B receives the marker. So B snapshots its state and forwards the marker to C. But then C is still hasn't received any marker from A, right? So it doesn't snapshot, but prioritize events from stream A in what we call the alignment phase. Then eventually A receives the marker and snapshots its states, and then the marker arrives at C, where it's now time to snapshot and forward until the whole graph of tasks snapshots their states. Now, in summary, I would say unaligned snapshots give the best runtime performance, but sacrifice recovery times due to the redo phase that is needed on recovery. Then aligned snapshots are might be slightly slower due to the alignment phase, but they also have good properties. First of all, they reflect a complete execution of an epoch. So a snapshot is basically something that has no extra side effects to replay. And that's ultra useful if one needs to actually use the snapshot for isolated queries or for snapshot isolation. Furthermore, those snapshots are the fastest to reconfigure, and recent work also showed the benefits of using the markers themselves as live reconfiguration points during the alignment phase. So in this paper called Chi from BLB 2017, they actually try that out and it works pretty well. So I highly recommend reading this work. So we covered some core advances in state management. However, there is more to come. So here I just enumerate a few interesting future directions. So one is we need to standardize snapshots to allow migrating pipelines across systems. And that's ultra useful, especially if users need to migrate, for example, from Beam to Flink to Spark and so on. Another idea is to allow external state access for stream tasks. So what can we achieve there? One can think of using stream states as live materialized views for database queries, or exposing a live set of ML features materialized in a streaming pipeline. And there are actually companies that start to do these things nowadays, such as Materialize, which is using Timely Data Flow, the new upgraded version of the NIAD system, to support Postgres compliant materialized views. Other topics that are really open include shared access to state and snapshot isolation for external ad hoc queries on stream state. And with that, I conclude my session, and I do hope that you enjoyed and learned something from it.